Now we're getting into more quantitative parts of chemistry, where we're going to be looking at quantities and reactions. We're looking at how much, if I have a certain amount of reactant, I can predict how much of a product I'm going to get. Or if I have a certain amount of product, I can predict how much reactant created it. And we know that this is all based on the mole. Because reactions occur with atoms and molecules, we can't really measure or detect atoms or molecules unless you have, like, really, really huge, expensive machines that can do that. What we can do is measure grams, or we can measure volume, that we know we have a certain amount of concentration of material in it. That we can do. We can measure that fairly readily. And luckily for us, a mole is just a way of measuring the amount of atoms that participate in a reaction. So chemical reactions involve atoms in a reaction, right? Like I said, but since we can't count atoms, we can count grams. And it turns out that a mole of an atom weighs exactly the same as its atomic mass units in grams per mole. So we call that the molar mass. And so that we can measure pretty easily. And early on in chemistry, scientists were able to recognize, by taking a known molecule with a known atomic mass and reacting it with an element that they'd just been discovered or something, but they didn't know what the atomic mass was. They could figure out what the new element's atomic mass was by looking at the ratios of how they reacted with each other and then measuring the amount of product. So atoms react with each other in whole numbers. What the hell is going on here? Come on. There we go. So atoms react with each other in whole number molar ratios, not mass ratios. So when I say that, like, 1 or 2 hydrogen molecules react with 1 oxygen molecule and make 2 water molecules, I'm not saying that 2 grams of hydrogen react with 1 gram of oxygen and make 2 grams of water. That's not the case, because that's not how reactions take place. Reactions take place between atoms, not masses. And so we need to know what the moles are. 2 moles of hydrogen gas react with 1 mole of oxygen molecules and make 2 moles of water. So we define a mole as the number of atoms in 12 grams of carbon-12. That is a mole. And so that number is this Avogadro's number here, which, again, I'm not going to ask anyone to remember. It's just a big number. So, because we're not going to count atoms, really. I'm not interested in the number of atoms participating in a reaction, because none of us are going to be able to measure that. We will be able to measure masses, and that's something that we're going to be doing a lot of in the lab. So just makes the point here again. We could always calculate the molar mass of anything by looking at the mass of all the atoms in a molecule. That's how we're going to do it. So for instance, water. If we wanted to know what the molar mass of water was, we would look up what the molar mass of hydrogen is, and multiply that by 2. And we look up the mass of oxygen and multiply that by 1. And that would give us the molar mass of water. And all these molar masses, as you know, are here on your periodic table. I'm going to look for a periodic table that has bigger numbers than this because I'm having a hard time reading it. But that's part of the information that the periodic table has for you. So when we're doing these conversions, we're going to be doing them back and forth. We're going to be converting from moles to mass and then from mass to moles, depending on what the question is. A lot of times we'll get a question something like, what's the mass of, 3.5 moles of something. So in that situation, we figure out what the molar mass is, and then we would multiply it by something like this, with moles on the bottom, so that would cancel, and we'd be left with an answer in grams. On the other hand, if we were given a mass of something and asked to consider how many moles that was, we would have a conversion like this, where grams are on the bottom. So we'd start with grams, we'd multiply it by moles over grams, get rid of our grams, and be left with moles. And then sometimes we're going to have to do a lot of these conversions in one problem, particularly if we're taking a gram of reactant, converting it to moles of reactant, converting that to moles of product, and then converting moles of product back to grams. So that's a lot of conversions, and we're going to be doing a bunch of those. So this just makes the point again. Whatever you need to convert, always put the quantity you want on the top. We've done that plenty of times, right? Whatever you want to have on the top, that's the unit that you want. And on the bottom, whatever it is, that's the one you want to get rid of. So if you want to get rid of grams, you use moles over grams. And if you want to get rid of moles, you do the same thing, but upside down. Okay. So we're going to be doing lots of these sort of things. It'll become like second nature. So let's do this one. I said I would do a couple of these with you. And here's the first one we'll do. So a chemist needs a certain mass of KMnO4. Anybody know what that's called? Should know what the K is anyway.
Potassium.
Right. And MnO4 is an ion called permanganate. Per meaning it has one more oxygen than expected. So MnO3 is manganate and MnO4 is permanganate. So if we want to know how many moles that is, we need to figure out what's the mass of this. And so we just look up the masses of each one on our periodic table. First, we need to figure out how many atoms of each one. So 1 potassium, 1 manganese, and 4 oxygen. So that's 1 times, what's the mass of potassium? Anyone have the periodic table in front of them?
39.0983.
Oops. 39.093 or 98? I think I have 98.
98.
98, right? Yeah. And what's the mass of manganese?
54.938.
938, right? And oxygen, I know that one. That's 15.999. So we just add this, and this is 63.996. So the total is 158.032 grams per mole. Now remember, carry all of these digits, carry as many as as you can. Do not round off in the middle of your calculation because we are not done. All we figured out is just the molar mass of potassium permanganate. So now we write down the other bit of information that we have. That's the mass. So 457.8 grams. And we're going to multiply that by something. And the answer we're looking for is moles. So where are we going to put moles and where are we going to put grams?
Moles on top and grams at the bottom.
That's right. So 1 mole is equivalent. And remember, each time we do one of these conversions, it's just an equivalent. The top should equal the bottom. So 1 mole is the same as 158.032 grams. My grams cancel, and I get an answer of 2.8919 moles. Now, am I done?
No.
What do I have to do? What's my final answer?
Your sig figs.
That's right. So how many sig figs should I report?
4.
4, right. There is 4 in 457.8. So I go 1, 2, 3, 4. And so what's my final answer?
2.892.
Yeah, moles. Correct. Excellent. So these are fairly straightforward because we're just doing basically one kind of conversion. It gets a little trickier later. So I want to talk about chemical equations because we're going to be dealing with these a lot. So one thing that you really need to know is that when you write an equation, your reactants are going to be here on the left side. So these are the ones going into the reaction, and the products are on the right side. And the arrow just tells you which direction the reaction is going. Sometimes the reaction can go in both directions. And so we have 2 arrows like that. But a lot of the time, a reaction will go to completion. That basically you will have no reactants left and everything will be products. So the other thing we need to know is that this must be balanced. So there has to be exactly the same number of atoms on this side, on the reactant side, and the product side. Have to have exactly the same number of atoms. And in other words, they have to have exactly the same mass as well. So whatever mass goes into the reaction has to come out. So even if you're burning wood, for instance, you have a big chunk of wood that's really, really heavy, and then you burn it and there's nothing left but ash and it's really, really light. And you think that mass is gone, but no, you have to take into consideration the mass of the carbon dioxide and the mass of the water vapor and everything else that turned to a gas. All those have to be accounted for too. So when we balance an equation, we have to make sure that you can see here that I have 1 molecule of O2 and I have 2 atoms of magnesium. And the reason is 1 atom of oxygen reacts with 1 atom of magnesium. And since there's 2 atoms of oxygen in that molecule, each one of them needs a magnesium to react with. So we have to change the coefficient here and here to make sure that it's balanced. So we'll be doing this a lot. And so one thing that I need you to remember, always, always, always check to see if a reaction is balanced. So like if you see, if I give you a reaction on a test, I'll give you something like this. It may not be balanced. Double check to make sure it is. I may have made a mistake and forgot to balance it, or I may have balanced it wrong. So without a balanced equation, we can't really do anything. That's the cornerstone of all these calculations. Have to have a balanced reaction. So always, always, always double check. Don't assume that the reaction is balanced, okay? So here's one here. I'm telling you that this is an unbalanced equation. So I'm sort of letting the cat out of the bag. Like, don't fool yourself. This is not balanced. So the question is, how many moles of water are produced? So this is what we want to know, moles of H2O. And the information we're given is 1.65 moles of ammonia is reacted. So ammonia is a reactant and water is a product. So how do we start balancing this reaction? What needs to change?
In progress.
Hello? What's not balanced?
Nitrogen.
Nitrogen isn't balanced, that's right. So we have one nitrogen on the reactant side, but we have two on the product side. And that's because nitrogen is more stable as a molecule by itself. So what do we do?
We can place a 2 before the at the reactant side.
Which one? Which reactant?
The nitrogen nitric, what's it called? The NH3.
NH3. It's ammonia. You can call it ammonia. Oh, sorry. I put a 3 there. Durr. 2. We want a 2. Okay. So that balances our nitrogen. What else?
Hydrogen.
Hydrogen is not balanced. Right. So how many do we have on the reactant side?
Six.
We have 6 now. So how are we going to get 6 hydrogens on the right side, on the product side?
We placed 3 before the H2O.
Yep, we would put a 3 there. Okay, so I've balanced my nitrogens, I've balanced my hydrogens. There's only one atom left. So where would that go? Only have oxygen left. How do I balance that? This one's a little tricky. So I have 3 oxygens on the product side. How many oxygen atoms do I have on the reactant side? Because remember, we're counting atoms, we're not counting molecules. So how many atoms do I have on the reactant side?
2.
2. So how do I get that to equal 3?
Did you add it to the NH3?
It's not going to help me get any more oxygens. The only source of oxygen is right there. That's the only source of oxygen. So I have to make that equal 3 somehow. So what am I going to multiply it by?
Would we need to increase it more to balance it?
Yeah, we need more. Exactly. We need more than 1 mole of oxygen molecules because I have 3 moles of oxygen atoms on the right side, but I have only 2 moles of oxygen atoms on the left side. So I need to multiply that O2 by something so I get 3.
What if we put a 2 in front of oxygen?
Then that gives me 4. Now I have too much oxygen on that side. I need to multiply it by something to give me 3. What would I multiply it by to give me 3?
1.5.
That's right. Or 3/2. And that's allowed. That's allowed when you're figuring out how much oxygen you need. When we're dealing with moles, it is more than fair to have 3/2. If we're dealing with atoms, we can't do that. There's no such thing as 1.5 molecules of oxygen. That doesn't make any sense. You can't have half a molecule. But when we're dealing with moles, that's totally fair. I mean, we could multiply everything by 2 in order so that we have whole numbers. And if we did that, we would have 4 NH3 plus 3 O2 make 2 N2 plus 6 waters. So we can do that if we're uncomfortable with fractions, but we can have fractions if we're dealing with moles. So don't feel bad if you have fractions. That's going to happen a lot when we're dealing with oxygen and nitrogen and chlorine and fluorine, because they are all diatomic molecules. So a lot of times we'll need 1.5 moles of them, or 1 1/3 moles of them, that sort of thing. So now we have a yes, question.
That was exactly what I was thinking, is that you would just increase the number to avoid putting the fraction, but so we can put fractions at any time as long as it's equivalent to what's on the product side.
If we're dealing with moles, yes.
For mole, okay.
If you're dealing with atoms, you can't do that. But our question's in moles, so it's perfectly fine. So now we take the information we have. We have 1.65 moles of ammonia, and we want to multiply that by something that gives us what we're looking for. We're looking for moles of water. Moles of water. So what is it I'm going to multiply this by to give me this? We just follow the same thing we've always done. We put the units we want on the top and the units we want to cancel on the bottom. So what units do we want on the top?
Water.
Not just water. What do we want?
Moles of water.
Moles of water, right. So we want moles of water on the top, and we want moles of ammonia on the bottom. So what is the ratio of moles of ammonia and moles of water? Where are we going to get that information?
From the equation.
Exactly, from the balanced equation. That's exactly where we get it, because the balanced equation tells us how many moles go in and how many moles come out. So from my balanced equation, what's the ratio of moles of water to moles of ammonia?
3 moles of water to 2 moles of ammonia.
Exactly, excellent. For every 3 moles of water we get that comes out, 2 moles of ammonia go in. So our answer is 1.65 times 3 divided by 2. And so I get 2.475 moles of water. Now, what's my final answer going to be?
$2.45.
Where does the 2.45 come from?
But you have to round off the
Well, how many significant digits do we have? Should we have?
3.
3, right? There's 3. The only number we have in the whole question has 3 significant digits in it. So this should have 1, 2, 3 significant digits in it. So the number we're going to round is this 7. So do we round it up or do we leave it alone?
I meant 2.48.
2.48, right, we round it up. So the final answer is 2.48 moles of water. Excellent. Okay. Now, here's one where we're given grams. And so we're going to have to do a couple conversions here. So the first bit of information we have is we have 17.5 moles of water are reacted. What's the first thing we should do before we even start this problem?
Make sure it's balanced.
Yeah, we should. Excellent. So let's have a look. So we've got 6 carbons on the left, and we've got 6 carbons on the right. So that's good. How many hydrogens do we have on the left side, on the reactant side?
12.
12, right. There's 6 times 2. So we have 12 hydrogens. And yep, 12 hydrogens on the right. So the only thing that's left is oxygens. So what's my total number of oxygens on the reactant side? I've got some here, and I've got some there. What's the total number?
18.
18. Excellent. Yeah, 12 here and 6 there for 18. And what about the product side?
$18 as well.
Same thing, right? Yeah, 6 there and 12 there. So it is balanced. So we're good to go. All right. So let's start. So I have 7. So the question is, I have 17.3 moles of water. And I want to know how many grams of glucose. This is glucose. So glucose is a monosaccharide sugar. Glucose, the simple sugar. So I want to know how many grams of that come out. So I made sure that the equation was balanced. What's the next thing I need to do? I mean, I could pretty easily find out how many moles of glucose are produced, right? That'd be pretty straightforward. But grams, that's going to be tricky. So there's information here I don't have. What do I need to calculate?
Molar mass.
Molar mass of what? Yes, you're correct. Of what?
Of the sugar.
Of the sugar, of the glucose, that's right. So that is 6 times carbon, 12 times hydrogen, and 6 times oxygen. So if you were in a hurry, you could just look it up, right? You could just look it up on Google. On a test, though, you're going to need to calculate it. So let's do that. So how much is a mole of carbon? What's the mass of a mole of carbon?
12.0107.
107? I think it's 11. Pretty sure. You might be right though, but I think it's 11. Did my calculation for 11, so I'm going to stick with it. What about hydrogen? What's the mole of hydrogen? Now remember, hydrogen atoms, not hydrogen molecules. We want hydrogen atoms. So what's the mass of a hydrogen atom?
1.008.
Yep,
I have a question.
sure.
So for that first one, it was, so on the periodic table, like some of them have 5 numbers behind the decimal. Sometimes they have 3. So
Mhm.
just for a good rule of-
Use as many as are there.
Okay,
Yep.
because I think that's where that number was, because I was gonna say the same thing. It says 12.0107. So it's just
Oh,
rounding.
07. Oh, okay.
Yeah. So it's just rounding, but I'm just wondering, because I noticed that often
Oh.
we're using 3 numbers after the decimal.
Yeah,
So
that's the periodic table that I've posted on
Yeah.
Canvas.
yes.
If you have a different one with more accurate masses on it, by all means, use that. Yeah,
Okay.
use the most accurate mass you can find.
Okay, sounds good.
Yeah,
Thank you.
because that'll help your answer. For instance, if you use 12.0107, your answer is going to be more accurate than mine. So go for it. And then oxygen, one I've memorized, 15.999. So then we just do the calculations, which I have done already. So 72.066. You can double check my math. 12.096 and 95. Yeah, 95.994. And we just add those up. And I got a total of 180.156 grams per mole. So that's for glucose, okay? Now we set up our equation. So we start with the information we're given. Pretty much the only information we're given is that many moles of water. So I'm going to need to multiply that by something. So what's the first conversion I need to make? I need to convert moles of water to what?
Moles of sugar.
That's right. That's right. You always need to figure out from the balanced equation how many moles are going in and how many moles are coming out. And so we want to get rid of moles of water and we want moles of glucose. So what, from the balanced reaction, what is the ratio of moles of glucose to moles of water?
One to 6.
That's right. 1 mole of sugar for every 6 moles of water. That gets rid of my moles of water. And now I'm left with moles of glucose. But I wasn't asked about moles of glucose. I was asked about grams of glucose. So now what do I need to do to get a final answer in grams of glucose? What do I put on the top? What do I put on the bottom?
180.156 grams on top and then 1 mole on the bottom.
That's right, because I want the grams. This is what I want to be left with. So I put the units of grams on the top and I put moles of glucose on the bottom. So that when I cancel moles of glucose, the only unit that's left now is grams, and that's what I want. And grams of glucose, that's important too. So 17.3 times 1/6 times 180.156. And I got for that 519.45 grams. So what is my final answer going to be?
$519 grams.
So where do you get your 3 significant digits from?
With the 17.3 moles of
That's
water.
right. Yeah, the only number you were given in the whole thing was how many moles of water. And there's 3 significant digits. So there's my 3 significant digits, and there's a 4. So I just leave it alone. So my final answer is 519 grams of glucose. Excellent. So when you're doing these mass calculations, that means you're going to be doing a lot of conversions. Because basically what that means is you're going to be starting with grams of substance A, whatever it is. It's either going to be a product or a reactant. You're going to need to convert that to moles of substance A, whether or not it's a product or reactant. You use the mole ratio from the balanced equation. That's why the balanced equation is so essential. Without it, you're lost. So that gives you the moles of the target substance, whether it's a product or a reactant, because the mole ratio means ratio of moles to moles, not grams to grams. And then finally, once you've got moles of your target, you convert that back to grams. So you need to do 3 conversions: grams to moles to moles, and then moles back to grams. So that's a lot of work. So let's finish with this. So this is a reaction with a lot of big molecules. So we have propanal, and when we are doing organic chemistry, we'll talk a little bit more about propanal. That has a group that looks like this. We call that an aldehyde. And when we have an aldehyde, we put the suffix al at the end. And when it gets oxidized, meaning more oxygen gets added to it, we get this. That is an acid group. We call that a carboxylic acid. That is an organic acid. So when it gets oxidized, it goes from this to this. That is coming up much later. So, but this is our reaction. So we're just going to assume that it's balanced because we don't have the other products there. Basically, this is our aldehyde. This is our acid. This is a molecule called potassium chromate. And it is very, very good at oxidizing things, which you could probably figure out because there is 7 oxygen atoms per molecule. And those oxygen atoms really like stealing electrons. So that does a really good job of oxidizing things. So the question is, if I react 135.8 grams of potassium chromate with my propanal over here, how much acid am I going to get? So I write down the information I have, 135.8 grams of potassium perchromate. So what do I need to do with this to start doing my calculations? What do I do with that?
Find out how many moles it is.
Exactly. I need to figure out how many moles that is, because I can't do anything with grams, because grams don't react with grams. Moles react with moles. So how am I going to figure out what the molar mass of that is? I mean, I could look it up, but if I'm doing a test, what am I going to do?
You look at each molecule.
Not each molecule,
Each atom. Each atom.
atom. There you go.
Yeah.
So how many potassium atoms do I have?
We have 2.
2.
4. Well, 2.
And then how many? No, we don't have 4 because we're just looking at, we're just looking at the mass of this. We're not concerning ourselves with the equation just yet.
Okay. Yeah.
We have 2 potassiums. How many chromiums?
2.
2.
And then 7 oxygens.
7 oxygens, right. So potassium has a mass of what? $39 what?
It's like 39.03. Oh, 09.
0.98. Yeah.
No,
0.98.
yeah.
And chromium I have as 2 times 51.998. And my old friend oxygen, 15.999. That will stick in your head because pretty much every organic molecule is going to have some oxygen in it. So oxygen gets around. So this is 78.196. This is 103.996. And this is 111.993 for a total of 294.185. Hopefully I got that right. Okay. What other information am I going to need? What's the next thing to do? So I've got my grams. Whoops. So I'm going to multiply this by something to give me my moles. So how do I convert this to moles?
You're going to divide it by the 294.
I never divide.
Well,
Never,
multiply.
ever divide. What do I put on the top?
Well, more.
Moles, yes.
Yeah.
Yeah, I never divide because then I get into trouble with my units. So I'm just going to call that K2. And my molar mass, 294.185 grams. So that gets rid of my grams, and I'm left with moles. What's the next conversion I need to make? So now I've got moles of this. What do I need to calculate next?
The ratio between the two molecules.
That's right, exactly. Because I'm being asked how many grams of this am I going to make? So it's moles of acid over moles of the potassium salt. So what's my ratio of moles of the acid over moles of the potassium salt?
1 and 2.
That's right. So if there's no number in front of a molecule in the reaction, we just assume that it's a 1. And there's a 2 here. So that's a 2. So that gets rid of my moles of potassium perchromate. And now all I've got left for units is moles of propionic acid. But the problem is I wasn't asked how many moles of propionic acid are produced. I was asked how many grams, how many grams of propionic acid are produced. So I need one more thing to calculate. What's the last thing I need to calculate?
The molar mass of propionic acid.
Exactly. And so I won't go through this one again with you because hopefully you know what you're doing by now. So it's 2 moles of carbon. It is 3 plus 2 plus 1, 6 moles of hydrogen and 2 moles of oxygen. You may wonder why it's written like that. Organic chemists write it like that so they know what the group is at the end. We call this a functional group. It's the one that does the chemistry. So this is an aldehyde functional group. This is an acid functional group. So that's why organic chemists will write it like that, because they're not terribly interested in this part. They're interested in the part that does the chemistry, which is the part with the oxygen in it. So the mass of propionic acid is 62.068 grams. for the acid. So where do I put the mass and where do I put the moles?
Mass at the top, moles at the bottom.
Right, because I want my answer to be in grams. So 62.068 grams on the top, 1 mole per mole of propionic acid. So I have moles of acid on the top, I have moles of acid on the bottom. And now the only thing I have left is grams of propionic acid, and that's what I want. So now all I have to do is multiply everything on the top, my 135 and my 1 and my 1 and my 62.068, and then I divide it by 2.94 and 2 and 1. And my final answer comes out to 14.326 grams of propionic acid. So what is my final answer going to be? I'll get rid of some of this up here so you can actually see what's going on. What should my final answer be?
14.33 grams.
That's right. Excellent. There's four significant digits in my amount of potassium chromate. So 1, 2, 3, 4. This is a 6. So we round that up, 14.33 grams. Great. Yeah. So when you're doing these sort of problems, have a big piece of paper and use as much space as you want. As you can see, I do it like erase a lot of it because there's a lot of information there. Yeah, so when I do it, I basically like take up a whole page and just make sure that I've got everything written down, that all my units balance out, and that I don't make a silly mistake of like flipping grams and moles when I should have moles over grams. That's why I never, ever, ever, ever divide. I always multiply, and I always have the units in there. So, because if the units don't cancel, I've done something wrong. If I'm left with like moles over moles at the end, then I did something, didn't do something right, because moles over moles will cancel and I'll have no units at all. So don't want to do that.
I have a question.
Yeah.
When you were talking about never divide, like what did you mean by that? Because like if you do 135.8 grams of this potassium salt, and then times 1 mole over 294.85, like what are we supposed to go through that? Like, do we just times that?
Yeah, but I didn't notice. I didn't divide. I multiplied.
Yeah.
One over 294. That's what I mean.
Oh, you multiplied over 294, and then when you multiply 294, you replace
multiplied it by 1 over 294. It's the same thing as dividing
That's the same
by
thing.
294. I just don't set it up that way. Yeah,
Okay.
so I always multiply, because that way I can see where my units are going. Because if I just divide it by grams, then grams would divide by grams and I'd have no units, but my units would be gone. So that's why I don't divide. I always multiply. So I have units on top and I have units on the bottom. That's what I mean by don't divide. Obviously, you need to divide with your calculator at some point. But I just mean when you're setting up the equations, don't divide. Set them up as multiplications.
I'm still kind of confused on like the moles of COH of that one acid over
moles of this, right?
Yeah, over the 2 moles of the potassium salt.
Okay.
And how that got us.
Oh, because there's 1. We just assume there's a 1 there, and there was a 2 there. Meaning for every 2 moles of potassium chromate that goes into this reaction,
you get 1
mole of propionic acid comes out. So that is this right here, 1 over 2.
Okay.
Because I have moles of potassium chromate here, and I have moles of potassium chromate here, and they cancel out. And I'm left with moles of the acid. And then as a final step, you just take the moles of the acid and then convert it to grams of the acid right here.
Okay.
Now, believe me, you'll have a lot more chances to do these. This isn't the last time you're going to see a question like this. Believe me. So you just want to see how to set it up one more time?
Yeah.
Okay.
Because like there's a lot going on.
Yeah, there is, isn't there? All right. So first, we get a question like this when we're given a mass of something and we're asked to predict or calculate the mass of something else. It means there's three things we need to do. We need to convert the mass of this to moles. Then we need to figure out how many moles of product we're going to get. That is a mole to mole ratio. That comes from the balanced equation. And then finally, when we have moles of product, we need to convert that back to mass. So there's three different calculations we need to do. So we start with the information we're given. And we're given 135.8 grams of the potassium salt. So the very first thing we do is convert that to moles. So the molar mass of the potassium salt is 294.185 grams per mole of the potassium salt. So this way I can cancel grams of potassium. That goes away. And now I'm left with moles of the potassium salt. So far, so good. That's the first thing I've done. Next thing I have to do then is convert those moles of potassium salt to moles of the product, because this is what I'm asked to figure out. I'm being asked how much propionic acid is produced. And I can only do that if I know the molar ratio of my reactant going in and my product coming out. That is from the balanced equation. So what I want is moles of propionic acid. And what I want to get rid of is moles of the potassium salt. In order to do that, I look at my balanced equation and I see what the ratios are. What are the molar ratios? Well, for every 1 mole of acid that comes out, 2 moles of potassium salt went in. So 1 to 2. So now I can cancel moles of potassium salt. And I'm left with moles of product. So far, so good. I've done 2 changes so far, but I'm still not done because I wasn't asked how many moles of propionic acid. I was asked how many grams. So finally, I convert these moles of acid to grams. And I do that by taking the molar mass of propionic acid. And I've done that calculation already. It's 1, 2, 3 carbons, 1, 3 plus 2 plus 1, 6 hydrogens, and 1, 2 oxygens. So you just add those together and you get 62.068 grams per mole. So with that information, I now multiply by, now I want grams at the end. And I want to get rid of these moles. So I'm going to put moles of acid on the bottom and put the molar mass of the acid on the top, which is 62.068. So I have moles of acid as a numerator. I have moles of acid as a denominator. And now the only unit I have left is grams of acid. That is what I want. So now I do my math. So this is on the top. This number's on the top. This number's a numerator. This number's a numerator. This number's a numerator. I multiply all of those together. That's my numerator. Now I multiply everything that's a denominator. So this is a denominator. This is a denominator. And that 1 is a denominator. So I multiply all of those together. And then I just divide the bottom and the top. And my final answer is 14.326. What are my units? Grams. Of what? Of acid.
Oh, okay, I get it now.
Yeah. And then the last thing to do is how many significant digits should I give my answer in?
4.
And I see it's 4. So I go 1, 2, 3, 4. That's a 6. So I round this to a 3. 14.33 grams of acid. Yeah, that's why I say you need a big piece of paper because you're going to be doing a lot of calculations for these. This is the sort of question on a test that's going to take you like, a good 20 minutes to do. So
Thank you.
strap in. No problem. That's what we're here for. We're learning. So basically, to sum up, we always check to make sure that the chemical equation we're using is balanced. That is so important because that just all it does is relate the number of moles of one substance in a reaction to moles of other substances in the reaction. So if we're given one, we can always calculate the other, but only if we know the molar ratio. And remember, that's never a mass ratio. Never, 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 never. It's always a molar ratio. So when we're doing a mole to mass calculation, we're taking the number of moles of a substance and then figuring out the mass of something else using our balanced chemical equation. And then in a mass to mass calculation, we start with the mass of something, convert it to moles, go to the moles of A, convert that to moles of B, and then back to grams of B. So like we just did. So it takes 3 conversions. So that was basically that. So any questions about that before we start the work? Does everybody have the worksheet for tonight?
Yes.
I can put it in the chat if you don't.
Yes, please.
Okay, let me do that. Isn't this like stoichiometry? It is stoichiometry. You didn't look at the slides from the lecture. I got a great picture of Captain Picard just bashing his head against the table, thinking about stoichiometry. Of course, man, with my shiny head, I'm looking more and more like Jean-Luc Picard every day. So yes, let me find that and put it in here. Did it go in there? In there. There it is. Now, next week, there'll be a lot of these questions. This week, there's some, mole calculations and a little bit more on molecular shapes. So what I'm going to do is get everyone into your rooms. And I'm going to go tuck in my son, and I'll be right back. All right, there you go. I will see you in a minute. All right, so sounds like not a lot of people got to the shape question. So I sort of wanted to start there because I think most people handled the mole conversion problems pretty easily. So the information you needed for part C was just the density of iron. So you just looked that up. I think it was like it's around 8 grams per cubic centimeter, something like that. And then the trick for E here was that chlorine gas is a molecule of chlorine, not chlorine atoms. So that is Cl2, because atoms of chlorine are inherently unstable. And if you have a bunch of chlorine atoms, they're just going to stick together and form chlorine molecules. That's stable. So chlorine gas is this. So the molar mass of chlorine molecules is twice as much as that of chlorine atoms. So I think most people got that one too. And this one I stupidly asked on the last. I put the same question in twice in a row. So if you missed it the first time, you're going to miss it the second time.
Can you go over this one?
What?
Can you go over this one?
Oh, sure. Yeah, so just briefly, so I really want to get to 3, is we write down what we have. So we have 25 mils. The density, butane is a gas. If you have a lighter, that's got butane gas in it. And so the density is 0.6011 grams per mil. So now I've got grams, but I want moles. So finally, I want moles on top and I want grams on the bottom. So that is a molar mass. I want to convert mass of a substance, in this instance butane, to moles. I have mass and I want moles. So I'll put moles on the top and my molar mass is 58.12. So now I just multiply 25 by 6.011 times 1 and then divide by 58.12. And you'll notice grams cancel out and the only unit I have left is moles. And then my answer should have how many significant digits?
3.
3, right. That has 3. This has 4, and this has 4. But when you're doing multiplication or division, you're always sort of stuck with the number that is the smallest number of significant digits. Okay?
Okay.
All right. So this is where things got confusing. So I have a file in Canvas under chapters 3 and 4 that has the rules for molecular shape based on the AXE rules that we went over like a couple weeks ago. So A is the central atom, X is the number of bonding regions around the central atom, and E is the number of lone pairs around the central atom. So then all you have to do is draw the Lewis structure and then figure out how many bonding regions are around it. And remember, it could be single, it could be a double, or it could be triple bond. And then how many lone pairs are around it. And then look up the shape on the table. So I put the table in the chat, but then I don't know what happened to it. I can put it there again. So where? Oh, I can't do that while I'm sharing. Anyway, it is in Canvas. I can also show you what it looks like. It's this file here. It's just a summary. It's called Classes of Molecular Shapes, brackets AXE. So all you have to do is figure out A is who's the central atom, X, how many bonding areas are around it, and how many lone pairs does it have. And then you just look up which one it is. So for instance, if there are 3 bonding areas and no lone pairs, it is trigonal planar. If there are 3 bonding regions and 1 lone pair, it is trigonal pyramidal. So that's the sort of thing we're looking for. So one other thing that I didn't really spend enough time on, I realized, is drawing these Lewis structures. We did really simple Lewis structures, but I haven't done any really that violate the octet rule. So I sort of want to go into a couple of these that violate the octet rule, so you're not scared when they show up. And the first one, the very first one, violates the octet rule. So I've sort of warned you that if you see sulfur or if you see phosphorus, good chance the octet rule's getting violated. So let's draw it. So we put S in the middle, sulfur, because it is less electronegative than oxygen, and there's only one of them, so it's probably the middle element in the middle. So I put my 3 oxygens around it, and then I connect them with a single bond, because I know they have got to have at least 1 bond. So what's the total number of valence electrons we would have present here?
24.
Right, because they're each oxygen and sulfur are both in group 6. So then there's 4 of them, so 24 total electrons. And we've used up 6. 1, 2, 3, 4, 5, 6. Remember, each bond is a pair of electrons. So we've used up 6, so we have 18 left. So when you have electrons left over, where do you start putting them?
Decorate the outside.
Exactly. So let's do that. So 2, 4, 6, 2, 4, 6, 2, 4, 6, and I'm out. No electrons left. So what I haven't made apparent enough to you is a concept known as charge. What is the charge on these atoms when we put the electrons on them? And the charge, the formal charge, is how many valence electrons does the atom have compared to the number of valence electrons it normally has. So how many valence electrons does oxygen normally have?
6.
It normally has 6, right? 6. And the other thing I haven't really explained very well is what we consider a valence electron in a Lewis structure. So in our Lewis structure, we consider a valence electron any electron in a lone pair. That makes sense. But we also consider one of the bonds, one of the electrons in a bond to be a valence electron too. Because basically we're looking at how many electrons can that atom claim as its own. And in this instance, each one of the oxygens can claim 2, 4, 6, 7. And so it can claim ownership of like 7 electrons, but it normally only has 6. So we would take the 6 electrons, 6 valence electrons that it normally has, and we would subtract the 7 electrons that it actually has in this structure, and that would give us the charge. And so the charge is -1. So each one of these oxygens has a negative charge. 1, 2, 3. Now let's look at sulfur. How many valence electrons does sulfur normally have?
6.
Same number, right? Same number.
Yeah.
Should have 6. Now, how many electrons can sulfur claim for its very own?
3.
Only 3, that's right. 1, 2, 3. So 6 minus 3 is +3. So this sulfur would have a +3 charge. So you can see the problem is I have a molecule with a ton of charges in it. And that's not stable. I've got a whole bunch of negative charges on the outside, and I got a big positive charge in the middle. Well, we can't have that. That's not very stable at all. Because what happens when you have a negative charge and a positive charge next to it, where do you think the electrons are going to go? Where do electrons like to go? What charge are they?
Negative.
They're negative. And if they see a positive charge right next to it, which direction are they going to go?
Towards the positive.
Toward the positive in a pretty big way. So what's going to happen? The
They
other
spend more
issue,
time.
they're all going to go to the middle. The other issue with this is that sulfur doesn't have enough electrons total. Sulfur's only total electrons is 6. It has this bond, 1 bond, 2 bonds, 3 bonds. It only has 6. It doesn't have a full octet. So that's the other problem with this particular structure. So we need to solve that. And the way we do is by moving a lone pair from each oxygen to the middle, like this.
Oh.
So this lone pair, whoops, this lone pair goes to the middle, this lone pair goes to the middle, and this lone pair goes to the middle. So what we're left with, this lone pair now turns into a bond, this lone pair turns into a bond, and this lone pair turns into a bond. So I have a double bond here, a double bond there, and a double bond there. So now, what's the charge on the oxygens? Let's calculate it. It should have 6 valence electrons. Well, let's count them. 2, 4, 5, 6. So the charge on the oxygens is now 0. So there's no charge in the oxygens. Now let's count the valence electrons in the sulfur. How many valence electrons does the sulfur have now?
6.
6, exactly. 2 there, 2 there, and 2 there for a total of 6. So now there's no more charges. So it's a much more stable molecule. The oxygens aren't charged, the sulfur is not charged. But I can't really see all of you, but I can see people are going to have an issue with this, because how many total electrons, not valence electrons, how many total electrons does the sulfur have now?
12.
12. That is a huge violation of the octet rule. That's 50% more than the 8 it's supposed to have. All the oxygens have 8, 2, 4, 6, 8. So they're not violating the octet rule, but the sulfur is violating the hell out of it. Is that allowed?
Yes, I think.
It is.
Yeah.
And why is it allowed?
Because of its position on the periodic table.
Yeah.
Where is it on the periodic table? It's in group 6. I know
Group
that.
6, yeah.
It has 6 valence electrons, but
Mhm.
that doesn't tell me about violating the octet rule, does it?
Is it because of its electronegativity?
Nope.
It's in the 3rd row.
It's in the 3rd row. There you go. It's in the 3rd period. Every time we add a period, we add a new shell. We add a new energy level. So in the first energy level, if you remember, there was room for 2 electrons. The second energy level, there was room for 8 electrons. But on the 3rd energy level, we have an S subshell, we have a P subshell, and we have a D subshell now. Every time we add a new energy level, we add a new shell. And this D subshell has room for 10 electrons in it. So the 3rd energy level has room for 18 electrons. So I can keep stuffing electrons in there until I completely run out of room. So 12 is not a problem. I have room for 18. So sulfur can violate the octet rule, and it often does. So like I've said, if you find sulfur or phosphorus, be prepared for the octet rule to get violated, because they do it all the time. And usually because they're bound to oxygen. So that's one of the reasons why it does that. So that's how you draw the Lewis structure. But now let's figure out what shape it is.
I have a quick question.
Sure.
So in order to know if it has a double bond, we're going to count how many electrons, or like figure out what the electronegativity is first, like if it's,
Well, the electronegativity is not
Balance.
going to help you with the number
Or
of
not-
bonds. It's
or-
the number of electrons.
yeah, that's what I mean, the number of electrons to make
Yes.
sure it's balanced, because you said there was -1 for oxygen, and then for sulfur it's 3+.
Mhm.
So that already is indication that we need to balance it, and that's how we know that there's double bonds.
Yeah, that basically tells you that the oxygens have too many electrons and the sulfur has too few. So originally, yeah, I had 3 negative charges around the outside and a +3 in the middle. So that tells you that the oxygens have more electrons than they need, and the sulfur doesn't have enough electrons. So electrons go from an area of abundance to where they're few. And they'll go from a place where there's a negative charge to one where there's a positive charge, because opposite charges attract. So that's what'll happen. Yeah. Yeah, we'll do some more of these. I realize I didn't go over formal charge at all. So and we haven't done violations of the octet rule. So I'll probably put some more in the worksheet for next week to give us a little more practice. So now that we know how to draw this, what shape is it going to be? So we're going to go to our AXE rule. So our central atom is what?
Sulfur.
Sulfur. And how many regions of electron density are around it?
Is it 3?
Three,
right.
yeah, because of
Mhm.
the period, yeah.
Yep. 3 regions. The region between each oxygen and the sulfur. So it has 3 bonding regions, 3 regions of electron density, 3 bonding regions. And how many lone pairs does the sulfur have?
None.
None, doesn't have any. So we put a 0 there. So AXE, X is the number of bonding regions, so that is 3. And E stands for lone pairs of electrons, and that is 0. So the shape is AX3. So then you would look up on the table that's in Canvas. So you should print it out and keep it. We look up AX3 and we find out that it is planar and trigonal, meaning 3. So basically it's in a plane and it's 3 regions. So this would be a planar molecule. So the next question is, would that be polar or non-polar? And why? And how do we figure that out? Whether it's polar or non-polar?
I said that it is nonpolar because the charge is equal across all of the molecule.
Well, that tells us that it's not charged. We can still have a non-charged molecule be polar. Water is polar, but it doesn't have a charge.
Oh, right.
So we need to figure out first dipoles, right? We need to figure out where the bond dipoles are. Now, who is more electronegative, oxygen or sulfur?
Sulfur.
I thought it was oxygen.
It's oxygen. Yeah, the 3 most electronegative elements are fluorine, oxygen, and nitrogen. So everything is less electronegative than them. So which direction are my bond dipoles going to go?
Toward the
What a-
sulfur?
Would it pull towards the oxygen because it
towards
has
the
higher
oxygen, right? Because
electronegativity?
it's more negative. And more negative means, if it's more electronegativity, it means these shared electrons are going to be pulled more towards oxygen than the sulfur, because electronegativity means it can pull on shared electrons more. So this is, the oxygens are all going to be slightly negatively charged, slightly, just a little bit. So this is what our bond dipoles would look like. One there, and one there, and one there. So those are our bond dipoles. Now, the question is, what would the molecular dipole look like? If we added all those together, what would we get? So if I added those three arrows together, what would I get? They're all the same size. So if you look at them this way, 1, 2, 3. So if I add those together, what do I get?
Non-polar?
Yeah, I get nothing, right? They all cancel out because this is completely symmetrical and they're all the same size. So if you have dipoles, bond dipoles that are all exactly the same size and they're all exactly symmetrical, they cancel each other out. So there is no molecular dipole and it is non-polar. In fact, sulfur trioxide is a gas.
So if it's polar, it would be if it wasn't perfectly symmetrical then?
Exactly. Yeah, if it's not perfectly symmetrical, then it's probably going to be polar. Like with water. Oop. So water, here I've got the bond dipoles look like this. They both point towards the oxygen, but they're not symmetrical, right? They're not, if they were symmetrical, they would be pointing directly at each other or pointing directly away from each other. This way, they're sort of both pointing down. And so when I add those together, I get a molecular dipole that looks like that because they add together. Whereas if they're all exactly the same size and they're arranged completely symmetrically, they cancel each other out. So shall we do one more?
Yes, please.
Because yeah, there's a lot going on here.
I have a question on the regions of electron density.
Mhm.
You mentioned that this one, it had 3
Yep.
regions.
Yep.
How did you come to that?
Okay. Because it looks like this. So the sulfur is the central atom. And so we look for regions where we're going to find regions in space where we're going to find electrons. And it doesn't matter how many electrons, it's just where are they? So here I've got 1, 2, 3, 4 electrons between sulfur and oxygen 1. So that's a region in space where I'm going to find 4 electrons. Same here. 1, 2, 3, 4 electrons in the region of space between the sulfur and oxygen 2. That's 2 regions, and then 3 regions. So regions just mean where you're going to find electrons in space. And they're either going to be bonding electrons or they're going to be lone pairs. So with water has 4 regions in space where we'll find electrons. There's a pair in space, there's a pair in space, there's a pair in space, and there's a pair in space. So that would be 4 regions of electron density, 2 of which are bonding, these 2, are
Mhm.
bonding, and these two aren't. Those two are lone pairs.
So then why don't the lone pairs on the first example count?
There are no lone pairs here. Sulfur has no lone pairs. All of its electrons are in bonds. So it has one,
But
two.
the oxygen had them.
Yes,
Is it,
but-
you're only,
Yes,
so you're
but they're
only
not
asking
on
about the
they're not the
central?
central atom. Yeah.
Oh, I didn't know that. Okay, so you're
Yeah,
only
yeah.
asking about the central atom. Okay,
Right, right. The shape is completely dictated by whoever the central atom is. And
just
then
the central
everybody,
atom. Okay,
and then everyone's arranged around that. Yeah, that's
Okay.
that's the confusion. Mhm.
got it. Thank you.
Yeah, no problem. All right, let's do this one. We had some fun with that one. So that is just written the way in the order that it's written. So you just go HONO, and then connect them with a bond. So in this one, the central atom is going to be the nitrogen, because we don't really consider hydrogen. It's so small, we don't really consider it to be an atom, really. So it's so small. So we consider the larger atoms, oxygen, nitrogen. I should just put a, if there's a test, I'll put a line under the central atom so you'll know which one it is, okay? So how many total valence electrons are we going to have here? Remember, you have to add up everybody.
18.
Right. So there is 1, 6, 5, 6 for a total of 18. And we have used up how many in bonds?
Six.
We've used up 6, right? 1, whoop. There you go. So 2, 4, 6. So I have 12 electrons left. So the easiest thing to do would just be to give each one of them 4. So why don't we just go ahead and do that? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now everybody, so that's all the electrons are gone. Now let's look and see what the charges would be and whether everybody has an octet. So here's oxygen 1 and oxygen 2, so we'll know which one we're talking about. So let's look at oxygen 1. How many valence electrons does oxygen 1 have?
Six.
6, exactly, excellent. 2, whoops. 2, 4, 5, 6. And how many should it have?
6.
6, so there's no charge. Does it have an octet?
Yes.
Yes, because it has 1, 2, 3, 4, 5, 6, 7, 8. And you'll see oxygen almost always will have 2 bonds and 2 lone pairs. So that oxygen 1 is fine. Now let's look at oxygen 2. How many valence electrons does oxygen 2 have?
5.
It has 5, right? 2, 4, 5. So that's 1 fewer than it's supposed to. So this oxygen will have a positive charge. So that's not good. And what about total
question.
electron? Oh,
So,
go ahead.
So the positive charge is because it's supposed to have 6 and then we minus
And it only
5.
has 5, right? So
Okay.
you write down how many this is supposed to have. It's supposed to have 6. How many does it have? 5. What's the difference? Plus 1. So oxygen with a positive charge is not a happy camper because oxygen is so electronegative. It almost never has a positive charge. Very, very few times will you see an oxygen with a positive charge. That's extremely unstable. So does it have an octet?
No.
No. How many electrons, how many total electrons does it have?
6.
6, right. It's got the 2 lone pairs for 4, and it's got these 2 bonds, these other 2 electrons in the bond for a total of 6. So it also doesn't have an octet. So that's not happy. So let's look at the nitrogen. How many valence electrons does the nitrogen have?
6.
It has 6. Very good. Man, you guys are getting this quick. So 2, 4, 5, 6. So it has 6. How many should it have? How many valence electrons does nitrogen normally have?
5.
Normally it's 5, right? So normally has 5. Now it has 6. So its charge is -1. And does it have an octet?
Yes.
It does. So it does have an octet. So that part of it's fine. But we have a problem because oxygen number 2 has a positive charge and it really doesn't like that. And it doesn't have an octet. So how are we going to solve that problem? And nitrogen has too many electrons.
Double bond
Nitrogen has a
between,
negative charge. So what do we do about that?
make a double bond between nitrogen and oxygen.
That's exactly right. We take this lone pair here and we share it with oxygen. So then this lone pair goes away and I get a double bond. And you should always sort of look for this kind of pattern because oxygen, what does it have? It has 2 bonds and 2 lone pairs. What does nitrogen have? Nitrogen has 1 lone pair and 1, 2, 3 bonds. And that's what it has here. 1, 2, 3. So now nitrogen has 1, 2, 3, 4, 5 valence electrons. So it now has no charge. And oxygen has 2, 4, 5, 6 valence electrons. And now it also has no charge. So this is our final structure. So it's going to look like this. Lone pair, lone pair, lone pair, 2 lone pairs here. So if nitrogen is our central atom, how many regions of electron density are around it?
I think you meant to write H, right? Because you wrote NO.
Oh, I did. You're right. It's all right. H. Here we go. Nice pull. So if nitrogen is our central atom, how many regions of electron density are around it?
3.
3. That's right. And how many are bonding regions?
2.
2. Yep. 1 there, 1 there. And how many lone pairs does it have?
1.
1. Right. It's got that lone pair right there. So when I write my AXE, A is the central atom, which is the nitrogen. And what do I put by the X? X is
2.
bonding regions. 2, right. And what do I put by the E?
3.
E is the number of lone pairs.
Oh, 1. 1. sorry.
1. So then I just look on my table for AX2E1. And what shape is that? Hopefully someone's got the table open.
V-shaped or bent?
Bent. Now, is this going to be polar or non-polar? Let's draw the bond dipoles. So who's more electronegative, oxygen or nitrogen? They're pretty close.
Oxygen.
I think oxygen's slightly more electronegative, I think.
The chart that's on Canvas, is that something also we should print and we can use?
Yes, definitely.
Okay, then
Yeah.
yeah, it's oxygen.
Yeah, oxygen is slightly more electronegative. So we're going to have two dipoles, bond dipoles, one here pointing toward the oxygen and the other one there. Now, this isn't really representative of the actual shape, is it? Because it's actually bent. So what we really should be, what it really would look like is this. With its lone pair there. Because remember, these regions of electrons in space want to get as far away from each other as possible. That's why it's bent, because I have a pair of electrons here, I have a pair of electrons here, I have two pairs of electrons there. So they want to get away from each other. They want to adopt a shape that puts the greatest distance between them. So this is the actual shape. So when I draw my bond dipoles now, they're going to look like this.
So the arrows that you drew, it's because nitrogen is moving towards oxygen, like in other-
Nitrogen is less electronegative than oxygen. So the
Okay.
little positive sign points towards where the fewer electrons would be, and the arrow points to where more electrons would be. So because oxygen is more electronegative than the nitrogen, this pair of electrons here that it's sharing are going to spend a little more time in oxygen's neighborhood than the nitrogen. So this is what the actual bond dipoles would look like. So is this going to be polar or non-polar?
Where's the hydrogen supposed to be?
Oh, the hydrogen will be over here.
Oh, okay.
Yeah. Hydrogen's not really important for this. We don't even consider the hydrogen because it's not connected to the central atom. So in this setup here, is this going to be not polar or non-polar? In other words, do those bond dipoles add together, or do they annihilate each other? Do they completely cancel each other out? So to answer that, are they pointing directly at each other or directly away from each other?
Away?
Is it directly away?
No.
It isn't, right? This would be pointing directly away from each other if they were equal and completely opposite. But these are not. They're both pointing down. So does that make it polar or non-polar?
Polar?
Makes it polar, right? Because these two, this, get a different color. This bond dipole here and this bond dipole there, when we add those together, we get one that's pointing away from the nitrogen and toward the two oxygens. That means we have a net dipole for the whole molecule. That means it is polar. Yeah, I swear we'll spend a little more time on this because yeah, I realize I haven't spent enough time talking about violations of the octet rule and formal charge. So that's sort of something we need to review a little bit.
I'm sorry, would you be able to go over the region of electron density, the bonding regions
Sure.
again, because I'm kind of confused.
No problem. So let's write this out. We'll just use the one we just did. So looks like this. So I got a lone pair there, a lone pair there, and 2 lone pairs there. So the central atom, we are considering it to be nitrogen. So we look at where in space are we going to find electrons around the nitrogen? Well, we're going to find them in 3 places. And these are the 3 places. 1, this single bond, that's 1 region. 2, this lone pair. And 3, this double bond.
Oh, okay.
That's a
Yeah, I was looking at the
that-
hydrogen and I was like, isn't it 4?
No, this isn't connected to the central atom, so we do not
Oh, okay.
consider it. Yeah. So that is 3 regions. 2 of them are bonding. So 1 and 3 are bonding regions. And we have a lone pair here. So that's 1 lone pair. So we go A, X, E. X is bonding regions. There's 2 of them. E is lone pairs. There's 1 of them. And we just look on our table and see what shape that is.
And bonding regions, how did you get that?
How do I get what?
How did you get the number of bonding regions?
Oh, there's 2 of them. There's a number 1 is a region where there's 1
Okay.
shared electron, and number 3 is a region where there's 4 shared electrons. But they're both regions in space. This region is between oxygen 1 and the nitrogen. And this region here is between oxygen 2 and the nitrogen. There just happens to be more electrons in.
So the oxygen
the
2,
third
that's
one.
not counted as 3 then, because the double bonded isn't counted as 2 different
Nope,
bonding regions.
nope, because it's a region in space where you're going to find electrons. That's
Okay.
all a region means. So regions of electron density, meaning where my electrons at. And my
In
electrons
comparison
are
to
in
the center
3
one.
places.
In comparison to the center element.
Sorry?
In reference to the center element,
The
correct?
center,
Okay.
yeah, the central atom only. We're only interested in the central atom because everybody is going to arrange themselves around the central atom, and that's what's going to determine the shape of the overall molecule. This hydrogen has basically no influence on the overall shape of the molecule at all. I mean, it's a single proton. It's tiny. It
Okay.
doesn't really take up any space, so it doesn't influence the shape, and it's not sharing any electrons with the central molecule, with the central atom, so it doesn't matter.
And so, how did you get whether it's polar versus non-polar? Like I understand that
Oh, okay.
oxygen pose more in terms
Because
of
we looked up what
electronegativity.
shape it was. AX2E1 was bent. And that means that this molecule doesn't actually look like this. It is not straight. It is bent. And so if we draw what it actually looks like, it looks like this. So here's my nitrogen. And then here's oxygen 1 on one side. And there's oxygen 2 on the other side. And there's the lone pair that nitrogen has. So it really looks like this. It's bent. And that makes sense because I've got 1, 2, 3 regions of electrons, and they want to be as far away as possible. So they're going to adopt this bent shape. So here's what the bend is right there. So now I draw my bond dipoles. Nitrogen is less electronegative than oxygen. So the bond dipole points toward the more electronegative element. And the same is true for this one. So then when I look at this bond dipole and this bond dipole, if I add them together, they don't cancel out. Because even though they're equal, they're not pointing exactly away from each other or pointing exactly at each other. They're both pointing away from each other, but at an angle. And since that's true, if I add them together, I get something that looks like this. That gives me an overall dipole, and that makes it polar. The other way to think about it is if there's a lot of electron density here around this oxygen, there's a lot of electron density around here around this oxygen, and they're sort of pointed away from less electron density here. That also makes it polar. There's a lot more electrons on the bottom of this molecule than there is on the top. That makes it polar.
So it has to, whether it's polar or not, has to, in part, has to do with the shape of the molecule.
Oh, it's totally by the shape of the molecule. Let's compare it to carbon dioxide. Carbon dioxide looks like this. So carbon is the central atom. How many bonding regions are around the carbon?
Two.
Two, right. There's one here. There's one there. It's for two. So there's two bonding regions. And how many lone pairs does the carbon have?
One,
How many?
0.
None, right, doesn't have any. Carbon rarely has lone pairs, almost never. And so we look, so that would be A, X, E, two bonding regions and no lone pairs. So we look up AX2, and that is linear. So what does that mean when it comes to the polarity? Well, let's draw the bond dipoles. Oxygen is more electronegative than carbon. So it's going to, bond dipole is going to point toward the carbon, or sorry, point toward the oxygen. And this bond dipole is also going to point towards the oxygen. But since this is linear, each one of these bond dipoles is exactly the same because they're both carbon, oxygen. The difference in electronegativity is exactly the same, but because it's linear, they're pointing directly away from each other at exactly 180 degrees. So they're equal and they're opposite. And when you add them together, you don't get anything. They cancel each other out. So carbon dioxide is nonpolar and explains why it's a gas. Nonpolar molecules generally become gases at room temperature, unless they're really, really big. We'll get into that. We'll get into that a little bit more later when we talk about interactions between molecules. But really small nonpolar molecules are going to be gases. Okay. I think everyone's had enough. When you guys get really quiet, I think I think I've tortured you enough. So any other questions before we call it a night?
Oh, I had a question.
Sure.
So in most of our work, like for example, with the one about butane, the one that's in both worksheets, when we're doing the answer, is your preference that we always do it in scientific notation, or is it okay if it's just the correct number?
Unless it says put it in scientific notation, you don't have to.
Okay.
But we did notice tonight that, let me go back. We did
But there
notice
is one problem that it's like super duper long answer, I think for number 1 in the worksheet for tonight.
Oh, that one?
Yeah. So would that one be in scientific notation? Because we can't.
1A, that's not going to be a large
It's
number.
not?
No.
Oh, okay. I think then we did that one wrong then.
Yeah, I mean, CO2 is a molar mass of 44. So it's like 9 times 44. That's not really that big a number for grams.
when
And
we
then you divide it by 1,000. So it actually should be less than 1.
Oh, I think we did the conversion opposite. We did it the wrong way.
Okay, but there was one that was kind of tricky. There was this one. Because I think, what was the answer for this one? Somebody had it. It's a fairly big number. It's not a huge number, but it's a big number. Anyone have the answer for that one? 'Cause that one turned out
Like
to,
6,200.
what was it?
Wait, for D or E?
E.
Yeah, I got 6,200.
But
I
the,
got half that, 3,100.
but what was the like total, all of the significant digits?
I got 8 for that big molecule. C6H.
Oh, sorry, for E, I'm looking at E.
Oh,
It
Three.
was 6,204.
Oh, that was it, yeah, 6,204 and grams. And when you look at the number of significant digits, what's the number of significant digits your answer should have?
3.
3, right. Well, that's the tricky part, because if I have 3, then my answer gets rounded down to 6,200. But what's the problem with that?
That's
must
a,
be 6,200 and then a little decimal point.
No, we can't do that, because that's
Oh.
4 significant digits. And they're only
Oh.
supposed to have 3.
So just put it in scientific notation.
There you go. Yeah. So I mean, I didn't realize that was going to be the answer. But yeah, if you need to show that this number has 3 significant digits, you have to use scientific notation to show that. So that would be 1, 2, 3, 6.20 times 10 to the 3rd grams. So I'll try not to be as evil as that on a test, but that just sort of happened.
Oh, I did want to ask you, I know next week we have our exam, I think next Wednesday, during lab. So we won't have a lab that day next week. So
Right.
how did you want us to show our work? Because you like us to show our work for the exam, but if the exam is via the computer,
No, it won't be.
oh,
No, I'm just going to give you, it'll just be like a worksheet. You'll just like write on it and then submit it like you would.
oh, okay,
So yeah, show all your work on it.
okay.
So I'll probably put it in the field like around 6 and then give you till 10 to finish it.
Okay.
Okay. Yeah, and people were asking about a study guide, so I'll do that on, I'll put that out on the weekend.
Will you also put out the key to the study guide?
The key for 1 and 2, I've already posted. I'll
mean, a
probably
key for the
do
study guide.
3 on Friday to give people enough time to submit 3. And then 4, basically we've done 4 tonight, so.
You meant the key for the study guide.
I don't know what you mean by a key for it then. What are you
Well,
referring to?
So the study guide will be example problems, right?
I'll just be like, what things are going to be on it.
Oh, okay.
If you want, yeah, if
Sometimes-
you want practice problems, I can put more of them on Chem 101. Or
Oh, and then that way
there's
we would
also
know the
practice
grade.
problems in your textbook too. I think the even numbers have solutions to them.
Okay.
All right. Okay. Night, everybody.